Okay, thanks for coming. So the title of my talk is processing billions of events in real time using the newly released open source software called Twitter Heron. Heron has been in production within Twitter for more than 2.5 years, and we just got it open source like a few months ago. And already we are hitting around probably 1,000 pull requests so far. I think we should be crossing it anytime next week, I guess. So anyway, so to give a context, I manage the real-time infrastructure group at Twitter that comprises of all the streaming analytics as well as interactive query analytics and real-time anomaly detections and a few more things like that. And so I also teach at Berkeley some of the undergrad CS courses in addition to doing some little bit of research. But other than that, so then before coming to Twitter, I was running my own company that got scooped up by Twitter, and I've been doing real time for probably around eight years now. Okay, so yeah, with that introduction, let me go into the talk. So I'll give you a first Heron overview, what it means, what it looks like, and some idea about how high-speed Heron is at this point, and also talk about a couple of issues that we encounter in the field, in practical experience, something called the Heron back pressure, how it does, and some kind of load shedding where when the data is coming at a real velocity and you want to be at the top of the real time always, when it starts lagging behind because of certain issues in the system, how do you go to the top of the queue always? Then I'll follow it by conclusion. So to give a Heron overview, how many of you have known Storm? Oh, nice. So essentially, you can think about Heron as a next iteration of Storm, except the fact that architecturally it has been changed drastically underneath, and but the terminology and the API we have kept the same. But the flexibility is that we can add a new APIs on top very quickly if we need to. But the architecture is sound enough that the code does not have to change. But anyway, I'll come to that later. So to give us terminology about the Storm/Heron. So a topology is a real-time job, and it's nothing but a DAG. And there are two types of vertices in the DAG, and there's one type of vertices is called the spouts, the other one is called bolts. And these vertices represent some kind of computations, and the edges within the DAG represents the streams of data that is flowing between these vertices. And spout essentially is a type of vertex which kind of taps into the data source and injects that data into the topology, which is essentially the real-time job. And the bolt essentially are processing elements in the sense like it takes the incoming tuple, transforms into whatever way it needs to be done, and emits an outgoing tuple. And some examples include filtering, aggregation, some kind of even streaming joins or stream table joins or stream service joins. And you can even do an arbitrary function where, for example, if I wanted to write my own machine learning algorithm where I wanted to classify a set of pictures based on the features that I've extracted out of it, right? So you can write an arbitrary function where when a picture comes in, it extracts the features, and after that, on the next stage, you can push the features out and it will classify what that picture is going to do. So with this terminology, let us look how a DAG looks like. So this is a typical DAG. So you have the couple of spouts, which in turn feeding into a next stage bolts, which are like 3 of them, bolt 1 through bolt 3. And once they're done with the part of the processing, then it goes to the next stage bolts, which is the bolt 4 and bolt 5. And the end stage bolts also capable of writing the results into another system. So that's one idea was that we could have introduced the notion of a sinks, like instead of a bolt, and you could have spout, bolt, and a sink. But so we wanted to kind of reduce the amount of new terminologies that we use. So instead, we just decided to keep the bolt term. But the bolt can do some kind of arbitrary processing, so which means they can overlap processing as well as storage the results into a third-party system simultaneously if that is would like to do. So to give a concrete example, let us take a word count topology. And in this case, what you're trying to do is you're going to count the number of distinct words on a live stream of real-time tweets that are coming at you. So in order to do that, you need to have some kind of a tweet spout that in turn taps into the Twitter firehose, where you can use the Twitter API to grab those tweets. And once that is, the tweets have been tapped, so the tweet has to be broken up into words somewhere. So that's why you introduce this parse tweet bold, where the tweet coming out of the spout is given to the parse tweet bold, which in turn breaks up into words. Then after the words are broken, the words have to be given to some kind of a bold called word count bold, which actually constitutes a logical plan. And so this is essentially a DAG in the database parlance. I mean, how many of you have taken the intro to databases or grad level database courses? There's a notion of a logical plan and a physical plan before the plan gets executed in the physical system. So we essentially claim this as more of a logical plan. But the thing is, because of the sheer size of data that you might be getting, you may not be able to handle that in a single process. Let us say like a tweet spout and a parse tweet bold and a word count bold, or a single process of each. Then you may not be able to handle the brunt of data in a single process. That's one possibility. Another possibility, even if you have multiple processes within a single machine, they may not be able to handle all the data that you get as well. So which means your physical execution has to be very different than what you look at in the logical plan. So in reality, the physical plan looks like this, where you have multiple number of tweet spout tasks and multiple number of parse tweet bold tasks and multiple number of word count bold tasks. And this is what we call as the parallelism. So you can give any number of parallelism for each one of those stages. So you can say I want like 50 instances of tweet spout, and I want 100 instances of parse tweet bold and 200 instances of word count bold, depending upon how much CPU, how much memory they need, and all the various things, right? So this is essentially what you call the physical plan when it gets realized in the execution stage. Now, this individual tasks are packed in some ways and distributed into a big cluster so that they can discover each other and start exchanging data from not only from within a single machine, but across machines as well. So I will go into those things a little bit detail. So now one of the challenges here is like when a parse tweet bold emits a data item or a tuple, which of the word count bold it should go to, because you have multiple tasks, right? So that is, how do we do it? So there is something called notion of what you call as stream groupings. And first is called the shuffle grouping, where it can pick randomly one of those bolds, downstream bolds, and send it to it. Then there is something called fields grouping, where you take the tuple and examine some of the attributes of the tuple, and based on the contents of those attributes, either you do some kind of a hash function or whatever it might be, and accordingly you direct the tuple to that appropriate downstream bold. Then the third one is something called all grouping, where you can replicate to everybody. And similarly, you have something called global grouping, where you have multiple tasks feeding off to one single guy. This is used for debugging and printing and all the various stuff. But 99% of the time, you have a combination of shuffle grouping and fields grouping is what we end up using. So now coming back to the word count topology, you can say that, by the way, a tweet spout, if it has to send the data to parse tweet bold, a shuffle grouping will suffice because anybody can parse that, break that tweet into words. But on the other hand, when you go from a parse tweet bold to a word count bold, you need to do fields grouping because you want the words of same words to go to the same mission or the same task so that you can compute the words accurately, right? So this shuffle and fields combination achieves the results that you would like to. So now, so why cannot use Storm? So we had a lot of issues with Storm, and we kind of summarized around 19 or 20 issues based on running Storm at scale and around for a couple of years. And that's one of the reasons why we decided to do Heron. And so some of the highlights are performance predictability. One of the various things was Storm was having a cluster of its own, and it had a scheduler of its own. And because of that, even though it was keep track of how much resources are available on each one of those machines, but it never enforces some kind of resource reservation in the sense hey, by the way, if we are given X amount of CPU and Y amount of memory, that's what you're supposed to use. You cannot go beyond that, right? So it couldn't enforce that. And because of that, we used to multiple topologies that were running and sharing some machines, they used to trample all over the place, and that leads to a lot of challenging issues that used to happen because during especially the events time, I mean, Twitter is known for real time, so during events time Oscar and Super Bowl, So those events, the traffic spikes up quite a bit. And because of that, like everybody starts occupying more CPUs. So then when they don't have a check on the amount of CPUs that they use, then they start trampling into the other, leading to all kind of performance issues. So that is the performance predictability. So next one is like improved developer productivity. So the debugging ability of a Storm was terrible in the sense like when the logs coming out of a single process, which consists of several threads, it's difficult to find out which thread actually emitted the message unless you go through all the logs. And especially if some threads are spewing more logs than the others, it's very hard to debug what the heck is going on. So that is, and second aspect is like you cannot even do a heap dump or some kind of what do you call attaching URKit kind of tool so that we can debug our performance profile, that spout or the bolt or whatever, so that you can identify your performance bottleneck. So then the third one is the ease of manageability. So we wanted to make sure that instead of running Storm on a separate cluster on its own, we wanted to go to multi-tenant cluster because as a small team, we have to support the entire Twitter's needs, right? That means like around 30 or 40 teams who are using the software or the infra. So what we have to do is to make sure that we don't have to maintain a separate cluster and the overhead that goes along with it. In fact, like when we were maintaining the same cluster, it took around 2 to 3 weeks to take a topology that was in development going into production because of the fact that we have to go through some kind of a cap planning to find out how much those machines are required for the topology, and we have to kind of send it to the cap planning or the hardware department, and which in turn will release the hardware. Then then somebody has to manually add those machines into the cluster or in the data center. Then it has to be, then some kind of entry has to be put in so that when the topology kind of describes or tells, okay, this is the topology, okay, you are entitled to only do this number of machines, right? So because of that, like it took like 3 weeks to 2 weeks in order to get a topology into production, which is unacceptable. So that so what we did is like how to make it easier and run it in a multi-tenant cluster. So because Twitter maintains a huge multi-tenant cluster which runs on top of Mesos, and we have the Aurora scheduler also, which I'm assuming everybody is familiar with it. So like which is probably around 60 to 100,000 machines, and all the critical services are running on top of those clusters. So if we can run it on alongside of those services, then we don't have to manage anything because there's one team that is managing the whole show. So some of the design decisions for Heron was it should be fully API compatible with Storm for obvious reasons, because Twitter had a huge investment in Storm and all its API and a lot of programs and the topologies have been written on top of it. There are a couple of frameworks that are run on top of it, which in turn generates those topologies automatically. So the whole machinery, we can't lift it by changing the API. So that is given is you have to API compatible. The second aspect is like a task isolation. As I said, we want isolation at all the levels. One is at the individual task level. Remember the parse, tweet, bolt, and the word count task. Each one should be having isolation of its own. And similarly, like when you pack a bunch of these processes into one container kind of stuff, then we need isolation at the container level. Then the individual topology should have isolation so that they don't share any kind of state with them, or so that it is even killing of a topology does not affect anybody else. So then finally, like we decided, like we use mainstream languages like C++, Java, and Python compared to some of the functional languages that Storm was employing in while they wrote the initial version, which is something called Clojure. I don't know whether you have heard about language Clojure. So it was written in Clojure, and Clojure and interaction with JVM leads to a lot of GC issues. And then we decided, okay, under the tools for Clojure was not that great. So which means as a developer, productivity is not that fast enough to deliver any new stuff and even fixing bugs and all. So instead, let's stick with mainstream languages so that we can get enough programmers. So with that, all those designations, the Heron architecture looks very simple. I mean, one of the system's principle is keep it simple. So that's what we did. Like, so we got away from the fact that, hey, we don't want any more schedulers, because already there are a lot of communities in schedulers that is working Mesos, Yarn, and Kubernetes. So there is enough momentum behind the scheduler communities. So reinventing the wheel for doing another scheduler is not doesn't make any sense. So instead, we piggyback on an existing scheduler. That scheduler could be anything, and as long as some mapping is needed to map Heron into that scheduler, then we are okay. So which means when you submit a topology, it looks like yet another job to the scheduler, and the scheduler in turn schedules the various topology based on the resource requirements of that topology. So that's what it is. So now let's drill down detail into more of how the individual topology looks like. So right from the start, we exploited the containers quite a bit. At the container level, we isolated several containers, and at the high level, there are two different kinds of containers. One is the master container, and another one is called data containers. So the ones that you see in the bottom are data containers, and the one at the top where the topology master is running is called the master container. So right from the start, we took advantage of the container architecture. Today, we use the C groups, but there have been a couple of PR requests to move to Docker kind of containers, and that is in the works. And so soon we will have a way by which you can package this as a Docker container, and it will be dispatched, and these Docker containers can discover itself in the mechanism that I will describe just in a minute. And then automatically everybody should start exchanging data. So when a topology gets launched in the first place, the master container is the first container that gets started. And the master container contains something called the Topology Master, which is the first process that comes up. And it looks at the DAG and how much resources it needs and everything, and also runs something called a packing algorithm. So which means like, hey, I need a total of 10 containers. How do I pack these parse tweet bold tasks and word count bold tasks and the tweet spout task into multiple containers, and so that everybody knows where that container they are running on. So that is called the packing algorithm. So once the packing is done, then the topology master in turn will request a scheduler. Hey, by the way, I need 10 containers, and each of the containers should be of 4 CPUs and probably like say a couple of gig of memory. So please give me those 10 containers, and automatically scheduler will tell you, okay, these are the machines on which the containers will be launched, and the scheduler also launches those containers. And once it launches those containers, then what happens is like the first process that comes up is what you call as a stream manager within each data container. And so the topology master, before launches those containers or even giving the request to a scheduler, it advertises itself saying that, hey, by the way, if anybody of my topology wants to reach out to me, this is the host and port that I'm listening on. So that location is returned in the Zookeeper cluster, which acts as a synchronization mechanism. Then once the data containers and the corresponding stream manager process comes up, the stream manager goes and looks in the Zookeeper cluster, hey, by the way, where is my topology master? So the moment it discovers where my topology master is, it contacts the topology master, hey, by the way, I am container X and I'm ready. So like a kind of a hello message, and registers itself. And so the topology master waits until every container that has been spawned has been reported in. And once everybody reports in, then it constitutes something called a physical plan. I mean, the logical plan is the DAG, which is already available on the Zookeeper. Then once every container reports in, they constitute something called a physical plan. And that physical plan consists of all the host and the port information where the stream manager is listening. Because you have to have a way by which the stream managers among different data containers have to discover each other so that the data exchange can happen. Because the data is flowing through this topology or the DAG, right? So which means some parts of the topology will be running on data container 1, and some parts will be running on data container 2, and so on. And because of that, like the data has to be moved around, and in order to move around, the stream managers have to discover each other. You can think about stream manager as more of a sophisticated data router in some form where it has to route the data to the appropriate containers. So once the stream manager has to discover each other. So that's why the topology master forms a physical plan. And the moment the physical plan is formed, and it stores the Zookeeper that physical plan into the Zookeeper cluster as well. And then it kind of broadcasts that physical plan to all the data containers or the stream managers. So once everybody gets the physical plan, they know the roles in the sense like, remember the stream manager will connect to each other, right? And also the instances, so which is essentially where your task is running. Like for example, a parse tweet bolt and so like word count bolts and all the various bolt are the individual tasks, were running as a single process. This is there is a huge distinction between Storm and Heron here is Storm used to run all these individual tasks as a thread within a worker, within a context of a single worker process, and that led to a lot of issues. And because that we wanted our isolation at various task level, container level, as well as topology level, so we made it each one the task as an individual process on its own, so that you can connect to it and query its memory, or you can heap dump it, or you can even do a performance profiling of the task without affecting anybody else. And also, you can do fine-grained resource allocation as well, because when you have one single process, how much resource you want to allocate, it's unknown to you unless you know what are the threads and other things are mapping, which is controlled by packing algorithms. In here, you can tell, like, hey, this process requires this much, and depending upon how the packing goes up, it will add up to the overall container resource that you need for the container. And so now once the physical plan is given to all the stream managers, and they know how to connect to each other, so they will form what you call a fully connected graph, so that they can start exchanging data. So that's how it starts executing. Now let us look at the failure scenarios, because it's all running in a distributed system. Process failure, machine failures are pretty common. So now let's take the example of the master container failure. So when the master container fails, there's nothing is affecting, because master container is more on the control path, not in the data path. So when the master container dies, so the data will continue to exchange on the data containers, except the fact that the topology master will be rescheduled in a different node by the scheduler, because scheduler comes to know, hey, that container died, so I have to give a different machine and different container, but of course it's the same container ID. So the moment the topology master comes in a different container or a different machine, so the first order of business it will do is look for in the Zookeeper cluster where my physical plan, logical plan, everything is. So think about the Zookeeper is essentially keeping the state of the master container, so that when the master container fails and comes back, it can rediscover its state. And that state includes the logical plan, physical plan, and the execution state that consists of who launches to topology, what time they launched, and what role they launched for tracking purposes. And so that takes care of the master container failure. I mean, another option is you could run multiple master containers with a kind of a master-slave relationship, which can be elected by Zookeeper also. But the thing is, in practice that we found out, as long as we can quickly schedule another container, you're fine. I mean, in practice, we have not seen any master container failure affecting, causing a lot of incidents. So we kind of stuck with it. So now let us look at the failure of a data container. So whenever a data container fails, topology master will come to know, because there's a keep alive messages that goes from the stream manager to the topology master. So the moment that the connection goes down, or the keep alives do not come anymore, then the topology master knows that the container is dead. So then another container gets spawned off by the scheduler, or based on the request from topology master. So then that container will come up, and the first order of business is rediscover where my topology master is, and send my host and port. Then once topology master gets it, it constitutes a new physical plan, because one guy has changed, because everybody has to connect to this guy. Then it saves it into the Zookeeper for the physical plan state. Then all the guys who failed the connection to the old guy who died will reconnect to the new guy. Then again, data will start exchange. And during the time, there is some amount of buffering going on, because if the container is average sized, because in a 24-core machine, the average size is somewhere around 4 to 6. So if you ask half the machine, or a 3/4 or a full machine, it's hard for the scheduler to get that machine quickly, because the time to allocate becomes longer the more the resources that you ask for on a per container basis. If it's an average size container, you won't even see a glitch in the failure and the coming back of the container, and all the physical plan and all the rejiggering. It's pretty quick. We probably will clock it within less than 20 seconds or so. So any questions so far on this topology architecture? Yes?
So the keep alive messages, how are they implemented? Are they in the user space?
So it is the stream manager has a direct connection to topology master using a TCP connection, and that connection is a control path connection, and then periodically it sends a hello messages. That's it.
So do you know how much of the traffic?
That is hardly because it does in every few seconds. So that is a configurable element. You can control it how much you want to, because obviously if the more interval that you configure, the more the failure reduction will go. So it's a trade-off that you have to play with. But that traffic is very small. So yes.
What do you use for service discovery?
Service discovery. So the Zookeeper essentially uses the service discovery. For example, if everybody, all the containers want to discover the Topology Master where it is running, the Topology Master has advertised itself on the Zookeeper, and the Zookeeper has a tree-like hierarchy, right? And in one of the hierarchy, it will have a topology name. Since everybody knows what topology name that they're running on, you key in on that path, then you know where the Topology Master is. Yes. Yes.
When the physical plan changes,
Mm-hmm.
when one of the data containers go down,
Mm-hmm.
does repropagation happen on other nodes? Or?
So like what happens is like when the data container goes in, like the tuples are being buffered, right? So you have two kind of semantics. One is our utmost ones, which is the best effort, like a regular IP kind of this thing. We keep pushing the data. If some failure happens, you're responsible for whatever you are doing. Then there is another semantics called at least once. So which means if some failure happens and the acknowledgement did not come back on time, then the tuples will be replayed so that the computation happens again. Right. So the Heron, as I said, Heron has been running in production for more than 2.5 years, and these are some of the topology shapes that we run. I mean, it is ranges from something very simple to all the way something complex. Like the simple topologies are typically people write it directly on the Storm API, but the complex topologies like this are being generated by a higher level framework that we use called Hummingbird, which is you write it in DSL, and the DSL spits out a topology, and some of the topologies look like this. So, and the largest topology runs around 800 containers or so. So that is equivalent to probably like 140 machines, I believe. So the single job runs on that, but since it is running on a multi-tenant cluster, it could be running on 800 machine, assuming each container maps into one single machine. So it has been tested in scale also. It just runs. So officially, like, has been in production for more than 2.5 years actually. Then I cannot give out the actual numbers, but yeah, like some of the jobs varies from 1 stage to 2 stage, 10 stages. The one thing that we did is after moving from Storm to Heron, one of the biggest things that we got is we got a 3x reduction in cores and memory. So we made the system so efficient in terms of moving data and all the various stuff. So we saw a huge reduction in cores. I mean, we were running around 3,500 nodes or something, around 4,000 nodes, and Storm, we brought it down to less than 1,500 nodes. Like, so that way, like, it's a huge savings from CapEx as well as the operational aspect of it. So that was one of the highlights of this thing. And so some of the use cases involves broadly like real-time ETL. I mean, for extract, transform, and load. So where the data is transformed and loaded into some other destination systems. And real-time BI. I mean, BI is essentially like where you have one of the applications is like when people are interacting with Twitter from a website or even mobile phones or different countries. So you can continuously view them at a second granularity where the traffic is spiking. Is it coming from UK or it's coming from Belarus and all the various things, and also broken down by what operating system people use, an iPhone or versus Android based on region. So you can see the entire breakdown of these various dimensions, and we use it as a Twitter command center where we keep monitoring all these graphs. So that's pretty cool. And we also do a lot of spam detection, product abuse, all the various things also on top of Heron, where they build some kind of a machine learning model and all the various things, and as the data coming in, they use to check against that model whether there is any violation or not. So that is all runs on top of Heron. And the trend computations, the trending hashtag trends and all the various trends that occurs, they're all computed on top of Heron as well. And in addition to that, some of the ML model buildings and model enhancements and model, and all the things also run on top of Heron. And as I said, media, like videos and pictures, if they want to classify based on certain things, they also pick up those media and extract the features and classify those features based on whatever the algorithms that you want to do. And the third one is it also is being heavily used for ops, where the data from the machines in the bigger clusters are continuously being collected, and we proactively look for if there is any machine failure or the impending machine failures. So these are the broad categories of uses. So like I wanted to highlight a couple of things that we did Heron reasonably right. So as you all know, the big data system is continuously evolving in the sense like, hey, tomorrow the new scheduler comes up and then that community goes away, then another scheduler comes up. Similarly, like today Hadoop is in fashion and tomorrow something else will be in fashion because Hadoop is being rewritten by Facebook in C++ because they wanted high performance or whatever, right? If they have open sources, that becomes a standard. So it's in a constantly changing environment of several components, how do you expect the code to be intact and we can move the code on top of these guys very quickly and easy enough. So one of the thing is like, so what we did is like, in order for inspiration, we looked at microkernels. How many of you know microkernels? Awesome, okay. So like I read that original paper on Mock. I mean, if you remember it used to be from CMU from early 90s. So I said like, they took the monolithic kernel operating system and stripped it down and say that, okay, this is the basic thing that we need. The rest of them can be run as a process, like even the pages and the virtual memory was running as pages, as long as the kernel has the basic IPC and the scheduling and other functionality. So I said like, why can't we do the same thing here? So if you look at streaming systems, they are nothing but data movers. I mean, they move data quickly as fast as can and schedule a computation, and this computation is moved to the next stages. So, which means the basic inter or infra IPC is needed, and also like what scheduler that you have to run on, because schedulers are also changing continuously, how the resource requested and the scheduling and monitoring those containers and all the various things. So we abstracted out into what we call as a service provider interface. Like a regular API, we invented something called SPI, which is service provider interface. And similarly, the state manager, which is the state synchronization point, similar to Zookeeper, that also is pluggable, because today you might be using Zookeeper, tomorrow if somebody will write based on something Raft, then they might have a different consensus algorithm. So we wanted to abstract that also out. So we have a state manager SPI and the scheduler SPI and the basic thing. So now all of them became a process on top of it. So which means like by well-established protocol using TCP and some kind of protobuf based protocols, everybody is interacting in a different way. I mean, through the IPCs. So if a topology master interacts with stream manager, there's a well-established protocol. As long as you conform with this protocol, you're fine. So this also allows a lot of flexibility where the topology masters are able to map quickly to Meso/Aurora, which is our production environment. And we are able to quickly, Microsoft was able to move that to run on Yarn very quickly within just 2 or 3 weeks. And then HPC community, which is on a high performance community, they use a scheduler called a Slurm scheduler. They were able to move it in a couple of weeks as well. And then after that, some people asked for Meso/Marathon. Oh, okay, that's also fine. So like the scheduler writing became so easy. And it kind of proved itself based on the various scheduler mappings. And so then also like going to a more process-like architecture. So for example, the instance that I mentioned where your tasks are actually running. So what happens if we wanted to tomorrow write your topologies in Python, right? So then I can write a Python instance that goes along with that API. That instance will run the native Python code in a Python VM. So we can write an instance in Python without affecting anybody else. That's what we did for Python API. And some guys at Adobe wanted to write a C++ topology. I said, go for it. As long as you conform to this protocol of instance, then you can run in your native. Because the reason why they wanted to go for C++ was they had some legacy code, which they wanted to wrap it up. And in addition to that, they also wanted to have a non-GC environment where it's running predictably, right? So because of those two main reason, they want to write it in C++, but so the architecture allows it. And tomorrow, if I wanted to change the stream manager to work on top of InfiniBand or even work on shared memory kind of architecture, yeah, you can just spin up, write a different stream manager and register it, then automatically it'll spin it up. So that way, this gave a very flexible architecture, and when the environment kind of surrounding it is continuously changing. So we published, finished a paper on this and submitted to ICD, International Conference on Data Engineering. It should be available anytime, like probably early in the first quarter or so. Anyway, so the plug and play component, as environment changes, code does not change. And so multi-language instances, as I mentioned, you can write Python in C++ and all the various stuff. And you can change the stream manager depending upon the transport or even processing semantics, at least once, at most once, exactly once, all kind of semantics. And finally, another important thing is it buys us a lot of velocity. So the guy who's developing stream manager versus the guy who's developing instance, they can run off independently and go at a faster velocity, and they can test it in their own environment and everything before they decide, okay, this is ready to go out. So there's no highly intertwined this thing. So that helps a lot. Even if you break one thing, doesn't mean that the other thing is broken, right? So I mean, so Heron actually runs on our development environments. We have this notion of a local scheduler, which we wrote so that it can run on a single laptop. And so we have the notion of an uploader where the jars and the other job execution code has to be uploaded, right? So that also uses a local file system, and that's our primary development environment. And the Mesos/Aurora is testing also. We use Zookeeper, and we test it with the HDFS uploaders, where you upload the job to HDFS. Then we have the production environment is purely in Aurora, and the Zookeeper is the state manager, and the Packer uploader, which allows you to do versioning management, where if your job you're uploading several times, it keeps a version of it so that if something happens in the new deploy, you can roll back. So those kind of things you can do. So now I'm going to go into what you call so even though it is written in this micro kernel-like-ish kind of architecture, did we sacrifice performance or what? So that is why I wanted to bring this up. Even though we went to more of a process model as compared to a thread model, did we lose performance because of that, or we are able to gain? So this is what it gives some more insight about what actually the cost is. So in order to do this experiment, we had an event spout, which is kind of tapping into one of the biggest data sources within Twitter. And then it sends it to the aggregation board where events are aggregated. So the way this is happening is the intake is around 60 to 100 million tuples per minute. And then it filters down to 8 to 12 million tuples per minute. And then after that, there is a flat map operation where it breaks the tuples into like 5x. So which means like the 8 to 12 becomes 40 to 60 million. Then that's what emitted out of the event spout. So the spout is doing all this logic of absorbing data, filtering, as well as expanding the tuple and sending it out. And the aggregate bolt takes the incoming tuples and it aggregates based on every second, then outputs into Redis, and that rate is around 25 to 42 million tuple per minute. And so this is the overall the resource consumed was like a Redis. We dedicated a machine for Redis, which is 24 cores, but the actual cores that were used was around 2 to 4. And of course, that machine contained of 48 GB. Now with Heron, which is running on a multi-tenant cluster, we requested cores of 120 cores. That is approximately around 5 machines. And the actual usage that we found was around 30 to 50 cores. And the memory requested was 200, but actually we used just only 180 GB. Now, when you break down where the heck the whole usage of the cores is, the cores are going, so we found out this was kind of unintuitive. The spout instances were the guys who were taking a lot of time. Like around 84% of the whole CPUs out of the 30 to 50 core usage, 84% went into spouts. And the bolts just took around 9%, and the Heron is overhead is just 7%, which is hardly like probably few cores out of the 30 to 50 cores, which is not much. So we were curious to find out like why this spout is taking too long. So we broke down the whole thing, and we figured out like the deserialization cost is 63%. So essentially, the data taking out of something like a Kafka or a distributed log that we have, taking the data out and deserializing, because we use thrift to represent the data, and deserializing takes the whole amount of cost. And partly because we found out our data is more nested. I mean, it's deeply nested from around 6 to 7 levels of nesting. And of course, we need to have some kind of a way for some kind of data evolution or a schema evolution so that we don't break down all the applications that were written with the older schema, right? So that is a necessary thing. But so we were kind of appalled to see that the deserialization cost is the major component of it. The next aspect is like getting the data out of Kafka itself, that took another 25% of the time because of the way they have returned their iterators and all the various things. And of course, the parse and filtering, which is the user logic and the mapping and a few things are not that much actually because of the noise. Then we broke down the bowls also, even though bowls don't have much of the overall usage. And so it again, writing data into an external system like Redis took more codes rather than anything else. And similarly, like now we clobber everything into something like fetching data versus user logic versus Heron usage. And the breakdown is, as you can see, the Heron usage is minimal noise. And yeah, so one more thing is like we recently did some more optimizations on Heron, and our throughput has increased by another 5x, and the latency has dropped by another 50 to 60%. So which means we can even have a higher throughput with low amount of CPUs. So the next problem that I wanted to do is like, what do you do, especially remember you're running the whole DAG in a distributed fashion, right? What happens if one of the guys is going slow? I mean, so this is what typically we call as stragglers. So the stragglers are a norm in the distributed system. We got to deal with it because they can occur for different reasons. And the first reason is bad host. I mean, in a 100,000 cluster, like some bad apples will be always coming up and going. So, but the thing is, since the streaming is something that you cannot stop, it keeps on going continuously. Because remember, the topology, once you launch it, there's no way to stop it unless you kill it. So it's not like an interactive query system where you type a query and the query finishes and the results come through. Whereas here, results are continuously being generated as long as the data is there to be generated. But the topology will still run if there is no data as well. So the first problem is a bad host. So if you're unfortunate that you got scheduled in a bad host, what do you do? Then the second one is execution skew. I mean, Twitter is known for skew because of the fact that the asymmetric nature of the user and their followers, right? So what do you do with the execution skew? Then if the topology is not adequately provisioned, then again stragglers could come in because you're not able to process the incoming data rate, right? So let's look at what are the approaches that we do in order to handle stragglers. So one is, by the way, the guy is not receiving as fast as I'm sending. Okay, so I'll just drop it. So that is essentially send it to straggler, drop data. So then on the other hand, the second approach is, hey, I will slow down to the pace of what the senders are absorbing the data from me. So everybody slows down. So that is the second approach. And this is very typical of TCP IP, where you have senders and receivers, and when sender starts with very fast, then if the moment the rate at which the receivers are sending acknowledgement, then they reduce the window size, like a TCP slow start and all the various things, right? And they settle down on speed. And the third one is detect stragglers and reschedule them. So that's the third approach. So like, what are the pros and cons of that? So drop data strategy. One of the biggest issues is unpredictable. You have no idea where the data is being dropped, especially in a complex DAG of like running on 500, 600 containers, right? So you don't have enough, it affects accuracy because since you don't know where it's being dropped, hey, by the way, I'm supposed to get a count of like a couple of million, but suddenly I'm getting something like a 500,000, which is not correct. But why it is not correct? So which means we don't have visibility into what is causing the issue, right? Because a lot of things could be happening. So on the other hand, the slowdown sender strategy, it kind of provides predictability because as everybody slows down for the slowest guy, the whole thing gets pushed into the source. That source is start lagging, where the starting point or the pointer at which you write the data versus the pointer that you're reading the data, it starts diverging because of the fact that I'm not absorbing the data as fast as I should. So, but when it comes back up, it reduces the recovery time and process data because moment if you identify that faulty host and reschedule it quickly, then it will go really fast to absorb the stuff. And it's also like handles temporary spikes because since the source is acting as a cushion of the buffer, it can handle spikes, like because Twitter is known for spikes, especially in the context of a Super Bowl and all. When a touchdown happens, boom, like it'll like 3-4x, it'll go in spike. Then again it'll come down, like it lasts for a few seconds, that's it. Then again, like some bad call of umpire, everybody, boom, it'll go up again, come down. So like essentially like the spikes are a kind of a norm within the Twitter's data sets that you get. And so this one handles spikes also nicely. So so we went with the slowdown sender strategy, and that we started implementing that. And so the way implemented is like, let me give an example, and illustrated by an example. So let's take this linear topology where you have a single spout, and that in turn goes to a bolt B2, which in turn feeds to a bolt B3, and finally it goes to bolt B4, which does some additional processing and storing the results. So this is how assuming 3 instances of each one of them, each one of the vertices in the node, let us say it's spread around 4 containers. As you know, like all the stream managers are fully connected graph, right? And they're exchanging data. Now let us say, take the example of B2 going slow, because B2 is not absorbing data from the other guys, and from S1s and other things as fast as it should. So what happens is the stream manager on that container will realize, because that is the guy who's pushing the data to the guy, B2, it will realize, hey, by the way, this guy is not going as fast as it is because my buffers are overflowing, because stream manager is the one which manages the buffer. And so then it sends a message, hey, by the way, some guy in my in my container is experiencing back pressure, so I'm going to initiate a back pressure protocol saying that, hey, by the way, everybody initiate whatever you need to do for back pressure, please go ahead and do it. So once all the stream manager receives that message, the first thing that they do is clamp down on the spouts. Because if you look at in the whole topology, the spouts are the sources of the data. By not absorbing data from the spout, which is that translates into essentially slowing down the topology in some fashion. Because all you're doing, the data in transit, they are only allowed to flow through, and we are waiting for the buffer to drain out of it. So once the buffers in the stream manager drain below a certain threshold, then we again send what you call relieve back pressure, then the spouts are open and keep going. So that is a very simple mechanism, and which allows you to go into initiate and relieve back pressure quickly. And also there is a cushion, in the sense like you have these buffers in the stream manager, and you can pick up the threshold on the what you call the low water mark and the high water mark, and accordingly set those values. And those values in turn will govern when the initiate back pressure occurs and relieve back pressure occurs. So if there is a huge gap between the two, then initiate and relieve will settle down to a smooth curve, rather than having something like initiate and relieve, like a flip-flop kind of thing, right? So yes.
How deep are those buffers?
So deep in the sense like how big?
How big, yeah.
So typically it's 100 meg.
100 meg.
Yes, 100 meg. But that's again configurable. So depending upon your application requirements and everything, you can configure on a per topology level also. So that seems to work well in practice. As if you look at that is a logical topology. This is like 15 containers. If one container is experiencing back pressure, the source will start lagging, because your read pointer will and write pointer will start lagging quite a bit. And at that point, what we do is you can manually restart a container. So we have a special command at the command line tool where you shoot down that container, and automatically scheduler removes that container the moment it knows that that container is the root cause of the back pressure. Because sometimes the back pressure most of the time the back pressure will recover itself automatically. And there are scenarios in which it doesn't recover at all because of high GC, something is happening. So then manual intervention will be required. So we are working on some kind of anomaly detection algorithms where, so automatically we look at all these various spout and other instances, and the moment something is behaving anomalous, and we look at the correlations and all the various things, then if there is high degree of confidence that that container is experiencing slowdown, then automatically shoot down the container and move on to the next host or whatever it is. So like the back pressure in practice, most scenarios it recovers, as I mentioned, without any manual intervention, which means no pager incidents. So the sustained back pressure occurs in some places, irrecoverable GC cycles or a bad or faulty host. Then finally, like sometimes user prefer dropping of data. They care about only the latest data. So we also run what you call for detecting bad and faulty hosts. We also run a separate Heron topology which takes the data and continuously does some kind of simple machine learning to figure out what is going on. Then now we are not automatically taking those hosts out of the scheduler. Instead, it goes through a manual process where it's given to the appropriate administrator. They in turn go manually remove it, but we will make it more automatic also. So finally, like this is load shedding. Sampling-based approaches, but it doesn't work very well because it's very hard to reason about sampling across uniform distributed spouts where everybody is reading in a different rates and everything, right? And we cannot upsample the results. And the upsampling results might not work for something like a median mode and all the stuff too. So we simply went with the drop-based approaches, simply drop the older data, the spout lags a threshold and takes a lag threshold and the lag adjustment value, and this seems to work in practice because here people, in these cases, people don't care about accuracy. Instead, they want to be on top of the real time. So because they might be trending, computing some trends or whatever it is. So even if, for example, in cases where we have seen some rack outages, right? So which means the data does not come for 4 hours. So when the data comes after 4 hours, then all the topologies who want to process the data, they will process, of course. But there are topologies where, hey, I don't care about what has happened in the last 4 hours. I want to know what is right now. So move my pointers directly to where the latest data is coming from. So that works. So if you want, like we have these 3 papers written already, and it's all available on the web. And if you wanted to learn about it, feel free to learn about it. And if you have any questions, please post them in Heron users mailing list. So we'll be happy to answer. So Heron is open sourced. If you guys want to use it, go for it. One thing that we guarantee is reliability, which is because we had after Heron went to production, 10x reduction in number of incidents. So the total number of incidents that we got in the 2.5 years is just 4. So like, and you can follow on Heron streaming. So the new active work that we are just wrapping up is what you call scaling. Automatically the topology can scale. And we have pretty much done it. It's in testing. And initially the rollout will be on manual scaling where you do a Heron update command, then it'll automatically expand the job from like 10 containers to 100 containers without pulling down the existing job. And that will become more automatic in Q1. So, yes, that's all I had. Any questions? Thank you. Supposed to be everything clear? I hear it. Okay, cool. Thank you.